Again, and this time it's for our last lesson in chapters 16 and 17. And this time we're going to look at the factors that can be changed to change the rates of reaction. So there are several factors that you can look at that are going to change reaction rates. And one of those factors is just the nature of the reactants. As we saw a little while ago, when we looked at the reactivity of lithium and sodium, potassium, rubidium, and cesium in water, we saw that as we came down the chart, we had some substances that were naturally more reactive than the others. So lithium was the least reactive, and then sodium, then potassium, then rubidium, and then remember, cesium, CS. And remember, cesium blew the side out of the beaker. A little dramatic there. So on the left side in the metals, as you come down, you get more reactive. Over on the right side, if we look at the halogens, coming up the halogens, we're getting more reactive. Again, we saw this a little while ago, and so we saw that iodine is less reactive than bromine, less reactive than chlorine, less reactive than fluorine. And so if you have the opportunity to change one of those reactants, then you can do so. But if you need lithium, for instance, in a reaction, you can't change to sodium and get yourself a little more reactive because of that. So this works only in limited situations. But as I alluded to yesterday in the previous video, concentration of the reactants, this is a concentration of the reactants, is going to affect the reaction rate as well. So thinking back to collision theory, more particles closer together lead to more collisions. You're just going to get more collisions. So on the right side here in this diagram, I have in A, I have a certain number of collisions, whatever the number of collisions is here. In B, I've doubled the number of B molecules, the blue, that's called B for blue, the double, the blue, times 2 in the blue. Now, if you go through and you count the number of collisions, that means we have times 2 in the number of collisions. And more collisions are going to give you more opportunities to react. In C, I have multiplied the red by 2. And again, if you count, and you can see the darker color, more red molecules closer together, the number of collisions is also multiplied by 2. And in D, I've multiplied the blue by 2. I've multiplied the red by 2. And when I put that all together, I get times 4 the number of collisions. So basically, we're working with the numbers game here. More total collisions will result in more collisions that are effective. So those are the collisions that have the correct orientation, that have the right amount of energy to reach that activated complex. But we have the same percentage of collisions that are effective. So if 20% of the collisions are effective before, 20% are effective before, it's just now we got 4 times the number of collisions if we have doubled everything. And so we're going to have a faster reaction just because of more collisions. Surface area, before I move on, what I want you to do is go and look at the first video now of the demos that I've got posted, and this is going to be the gummy bear demo. And in the gummy bear demo, we're changing the concentration of oxygen gas, and you can see what happens to the speed with which the gummy bear metabolizes Same sort of reaction that would be going on in your stomach, but a lot faster. And hopefully it doesn't go the way you see it in that reaction. Now, another thing you can do to change the reaction rate is to increase the surface area. So surface area is similar. Surface area tells you the interactions between the reactants. And we saw this back in dissolving as well, where we saw a very similar process going on. So if we take and we start off with this cube in this first cube, and let's call that number 1. If we then take that and we split it in half along all the faces, so splitting in half along all the faces, what do we end up doing? Well, we end up doubling the surface area. If we split it in 4s along all the faces, then we have 4 times the surface area. If we split it in this case into 8s, then we get 8 times the surface area. And so what we're doing is we're making smaller particles. The smaller we get, the larger the surface area is. And that's going to be for a given amount, whether it's a given mass or a given number of moles. So when we increase the particle, the surface area, what can happen is where I've drawn it in blue here, you can see that any reactant that's out here, so remember it takes 2 reactants at least, any reactant that's out here can now penetrate down into the interior, what used to be the interior, and now there's more interaction. So it increases the area of interaction. And therefore increases the number of collisions. And as above, increasing the number of collisions is going to increase the number of effective collisions. And that is going to increase the rate. So just playing with the amount of reactants you have there, you can increase the reaction rate. Suppose you can't change the number of reactants. Suppose you can't change the concentration. You're already concentrated enough, or other things are preventing that. What else can you do? Well, one of the things that you may think about is temperature. So why do you put food in the refrigerator or in the freezer to keep it cold? Why does that help? Because it slows down the rate of the decomposition reaction. So it turns out that a higher temperature is going to give you a higher rate. So what's going on here? So higher temperature means higher kinetic energy. In the collisions. So remember, temperature is a measure. Temperature measures kinetic energy. So higher temperature means we have a higher kinetic energy. Now, on the right here, I have a diagram that looks a little daunting at first, but let me explain what's going on. On the y-axis, we have the fraction or the number of collisions. And on the x-axis, we have the collision energy. So at any point along here, we could measure the energy. And then at any point along there, that would be the number of collisions that have that particular energy. And as we move higher in energy, so as we get higher in energy, we get fewer and fewer collisions with that amount of energy. And we get this big drop off, especially at this low temperature. I'll explain high temperature in a moment. Now, here is the activation energy. This is the minimum energy needed for the reaction we talked about yesterday. So only collisions that have this amount of energy or higher are going to be able to react. So only these collisions can be effective. We still have to worry about orientation, And orientation is nothing we can actually control in this model. There is something we can do. We'll talk about that in a moment. So we have this number of collisions that could be effective, the right amount of kinetic energy. When we go to a higher temperature, and let me change over to red, at a higher temperature, something happens. Higher temperature means a higher average kinetic energy. That means we need to shift to higher energies. So the number of collisions that have low energy comes down, but the number of collisions with high energy comes up. And because of that, now once we get out past the activation energy, we have all these extra collisions. It's really the area under the curve that we're looking at. The area indicates the height is the number of collisions times the energy is the total number of collisions in here. So we now have more molecules with enough kinetic energy to react. So let's write that over here. We have more molecules with kinetic energy that's sufficient to overcome the activation energy. Now, something you should also notice, it's not just a numbers game, it's the percentage. So the percentage also goes up. So we have a higher percentage of effective collisions. So not only have we increased the speed, we've increased the percentage of collisions that are going to give us enough energy. And as a secondary effect, there are also more collisions since the particles are moving faster, but this higher percentage is really the primary effect. And again, I want you to put a star on this. We have enough kinetic energy to overcome that activation energy. And the number of collisions that does that goes up. All right, so that's really all this diagram is showing us. So higher temperature, we have more collisions that have enough energy to react. Lower temperature, we have fewer collisions with enough energy to react. And so the reaction rate is higher at higher temperature and lower at lower temperature. Now, finally, we have something called a catalyst. You may have done a lab in bio last year where you took liver and you put it into a container of hydrogen peroxide and it started bubbling. Liver contains a catalyst. It's a biological catalyst, and we'll talk about biological catalysts in a few moments. Now, the primary effect of a catalyst is the catalyst lowers the activation energy. Let's change over to another color because it doesn't change the temperature. It lowers the activation energy, E sub A. So the reaction rate increases. What's the difference? The difference here is that you need less energy. Whereas when you change the temperature, higher temperature, you have more energy. But they both achieve the same effect. And here's how they do it. In the distribution up above, in that curve up above, what's going to happen is we're lowering that activation energy. So let's take it and say, let's put it at a new activation energy. Let's say right here, we have the activation energy for the catalyzed reaction. Catalyzed reaction, lower activation energy. Can you see that no matter what temperature, we now have additional number of particles, additional percentage of particles that have enough kinetic energy to react, whether it's at low temperature or at high temperature. So either way, there are more collisions and I'm going to try to squeeze this in with a higher, oops, I guess I could put it on the next line, more collisions and a higher percentage with that kinetic energy greater than this new, let me go back to green, this new lower activation energy. So that's what we're showing on the diagram to the right here. This diagram at the right, this is for the decomposition of hydrogen peroxide. It's an aqueous solution. And we actually saw this reaction in our reactions lab. So hydrogen peroxide, it decomposed into H2O, and let's put some balancing on here, which is a liquid, and O2 gas. All right, so uncatalyzed, this has a relatively high activation energy of 75 kilojoules per mole. I'm not sure where my units went. When we catalyze that reaction using iodide as a catalyst, the activation energy comes down to 58 kilojoules per mole. And that's going to be the next video you're going to watch. This is going to be the elephant's toothpaste. And go watch that video so you can see how this works as a catalyst. All right, so lowering the activation energy means we have a faster reaction. We need less energy. You need less. Am I still here? Yes, I'm still here. I went to a different program. I hope it's still going on. Okay, need less. I should say specify need less kinetic energy. Let's put a K in front of there. Need less kinetic energy to react. So that's one thing about catalysts. But there's something else about catalysts that's important that doesn't show in this reaction. And that is for something to be considered a catalyst and not necessarily a reactant. So catalysts do react. They do take part in the reaction. But in the end, the catalyst must come out the same as it goes in. It has to be regenerated in the end. And that's the third and final video. We call it the Pink Panther or the pink catalyst. And it's really a cool catalyst. It's a slightly different reaction. Don't worry about what the reaction is. But what you're going to see is that in the pink catalyst, we start off with some cobalt 2+, and along the way in the reaction, that cobalt 2+ turns green and becomes cobalt 3+, and it forms a new compound within the reaction before it lets go again and comes back and forms cobalt 2+. And I wish I had pink there because it is pink. I've been able to figure out how to get pink pens easily here. So we're stuck with red for the time being. So catalysts are able to speed up the reaction by lowering the activation energy. Now, we have something here, a really low activation energy, something called catalase. And this was the enzyme that's in liver. And this is what you would have used last year in bio. So an enzyme is just a biological catalyst. And the biological catalyst, the enzyme, can do two things. First, it does lower the activation energy. But the second thing it can do, and this is why life works so beautifully, is it can orient the molecules properly. And by orienting the molecules properly, the percentage of effective collisions goes up even more. So it goes up because of the lower activation energy, and it goes up because of the increase in effective collisions. Now, if you can speed up a reaction by lowering the activation energy, then you can inhibit or slow down the reaction So you want to slow down the reaction. Why would you want to slow down the reaction? Well, again, think about food. We talked about food in the refrigerator a little while ago, and lowering the temperature is going to slow down the reaction, right? If you can put something in the food that doesn't harm you to eat it, but slows down the reaction rate, then that's going to help to preserve the food. And so this would be preservatives. So whenever you read a food label and you see something is added as a preservative, that's actually chemically called an inhibitor. And what it does is it raises the activation energy. It blocks the original reaction from happening and makes that activation energy go higher, raises the activation energy, and that slows down the reaction rate. Okay, so that's what we need to know about changing the rate of the reaction. We have concentration. I'm going to skip over the first one with the nature of the reactions, because you can't really change most reactions. So concentration, surface area, temperature, and catalyst or the opposite inhibitor. And the homework will cover all of those. All right, so have a good rest of your day, and I will see you next time in class. Take care.